Hello everyone. We are going to consider today section 4.3, the method of undetermined coefficients for non-homogeneous differential equations of nth order. We just learned how to solve homogeneous equation, right? And generally speaking, there is nothing new in nth order in comparison to the second order. The only difference is that instead of two possible solutions for characteristic equation, you can have like n solutions, and they are going to produce slightly different functions, right? There's going to be nothing new in undetermined coefficients method as well. For non-homogeneous equations, generally speaking, we can use undetermined coefficients for next functions, e to the power of at. So exponential function on the right side, non-homogeneous, right? We can use it for polynomials of nth degree. We can also consider sine of bt and the cosine of bt, right? So we also can combine these functions either by two or all three of them together. And general idea is to search for a solution in a similar shape. Just leave some constant to determine them after substitution into the equation. So generally speaking, we are going to look for a particular solution. As we probably remember that usually general solution, y general solution consists out of homogeneous solution plus some particular solution yp. Basically, we already know how to deal with homogeneous solution. We just need to learn how to deal with a particular solution. And again, mostly the rules are same. There are some little features which I want to consider, okay? And those features are coming mostly from the possibility to have higher multiplicity for roots of equation. In second order equation, we had maximum multiplicity 2, right? We can have one real repeated root. Here we can have more than one repeated roots. Okay, so I'm going to consider an example. So we're going to start with example number 1. And example number 1 is the third derivative of y minus 3y second derivative plus 3y first derivative minus y equals 4e to the power of t. I'm choosing the simplest non-homogeneous right side, which is just an exponential function multiplied by some coefficient, like 4 can be any number actually, right? So we're going to start building characteristic equation. So we have r cubed minus 3r squared plus 3r and minus 1 equals to 0. Remember, homogeneous equation is going to use characteristic equation to find actually exponents or the frequency of sine and cosine functions, right? Well, you probably recognize a perfect square here. Perfect square means that we are going to have r minus 1 cube equals to 0. Well, just imagine r cube, then minus 3 r squared, then plus 3 r, first power of r, and minus 1. Well, again, remember the Pascal's triangle and the coefficients are 1, 3, 3, 1, right? So what we have here is 1 root r equals 1. Multiplicity is 3. What does it mean? It means that homogeneous solution, which is supposed to be c1e to the power of t, because we do have same root repeated 3 times, we're supposed to kind of have all different coefficients in front of t here, right? Exponential function, but we are not going to have it because we do have 1 here. We're going to solve this problem multiplying by t, so c2t e to the power of t and c3 t square e to the power of t. Well, you already know how we got t, right? You can kind of just multiply by t and see if it's working as a solution, or we had a proof actually that it's supposed to be t, right? How about t square? Well, we're just applying the same technique. This one is going to cover two possible solutions. We need three because it's a third order equation. So the third one, it's just the same way as we did the second one, multiplying by t. As our homogeneous solution, now we are going to search for particular solution. Well, as we see from the right side, particular solution supposed to look like a e to the power of t, right? But we already have homogeneous solution, which is same with this one. It's a constant e to the power of t. It's not good because if you take this solution, because it's the same as homogeneous, plug it into equation, because it's a solution of homogeneous equation, it's going to be equal to 0. You cannot make it equal to the right side. So you start thinking, okay, how we usually deal with this, we multiply by t, our standard technique, right? And we are going to multiply by t. And now we compare it with homogeneous solution, and we see that we do have already a solution multiplied by t as well as homogeneous solution. So we are going to continue multiplying by t and multiply by t squared. And we compare it to our homogeneous solution, and we see we do have t squared too. So it's still homogeneous solution. Well, why did it happen? Why we never had it in the second order? Because maximum multiplicity in the second order was 2. Here multiplicity is 3, and we use all three same roots. The only exit here is to make it cube, right? I'm going to erase 2 and write down 3 over here. That's going to be our particular solution. Now we are going to find the coefficient. That's all going to be a little bit complicated just because we have a product of polynomial or like power function and exponential, but I think it's not going to be super hard. So what I'm going to do, I'm going to calculate derivatives of this particular solution. So remember that that's a product rule. The constant is going to stay, but when you differentiate, don't forget that you differentiate exponential function. It's e to the power of t by t cubed. And then you differentiate t cubed, which is going to give you e to the power of t by 3t squared. And that's going to be the first derivative. Okay, I'm going to do a second derivative. A derivative of the first one, right? A constant is still outside. And I differentiate this one. It's a product rule, and that's going to give me e to the power of t cubed plus 3t squared. I differentiate t cubed e to the power of t. Now I'll need to differentiate this one, right? I'm going to differentiate the exponential factor first, 3t squared e to the power of t. And then I'm going to differentiate this t squared, right? I'm going to get 6 e to the power of t, just t. Well, again, we differentiate square, we get the first power, right? And the 2 multiplied by 3 is 6. Now the last derivative I'll need to solve this equation is going to be the third derivative. And the constant is going to stay as a. And these two terms are basically same, right? That's 3t squared e to the power of t. So I'm going to unify them into 6t squared e to the power of t. It's going to be easier for me to differentiate. So now I'm going to go back and differentiate this expression, and that's 3t squared e to the power of t. This one. No, I have to finish this one first. E to the power of t cubed, right? Differentiating e to the power of t. Now this one. I'll differentiate t first because it sits first here. 12t e to the power of t. I differentiated t squared, right? Plus 6t squared e to the power of t. When I differentiate the exponential factor, it's going to just keep me the expression. Now for this one, 2 terms, 2, right? Plus I differentiate exponential. It's e to the power of t, and I differentiate t, it's just going to give me just 6 e to the power of t. Looks crazy, right? I'm going to simplify a little bit this expression. I'll be able to substitute everything. It looks like this. So 3t squared, e to the power of t is going to be repeated in all terms, right? I'm just going to simplify the polynomial part. So what I have here, 3t squared, do I have more t squared? Yes, I have 6t squared too. So what I'm going to do, I'm going to erase 3 and add 6 together, right? So 3 plus 6 is 9t squared. This term is going to be t cubed. Now what we have, the term with t is going to be 12 plus 6, which is going to give me what, 18t, and the last term is just 6. sorry, and it's multiplied by e to the power of t. Well, what I'm going to do now, I'm going to, I guess, substitute everything into my equation and see what is going to happen. I'm going to scroll it a little bit up, so, but I don't want to go too far because I still want to see the derivative and the function, right? So first, as third derivative, well, this a and exponential are going to be repeated in all these derivatives, so I'm just going to put it outside. A e to the power of t here, right? So for the third derivative, I just need to copy it. I'm going to start with highest power of t cubed, right? Plus 9 t squared plus 18t and plus 6. So I did copy the third derivative. Now, 3 second derivative. So I'll need to multiply everything here by 3. The first one is going to be 3t cubed. And I'm supposed to put minus. I'm sorry, I put plus here automatically. There is a minus here, right? According to the equation. Next one, it was 6 multiplied by 3, it's 18, right? Minus 18t squared. And the last one, 6 multiplied by 3 is 18t, right? Minus 18t. So I did the second term, the third term, the first derivative. That's plus, right? Multiplied by t cubed, 3t cubed. Right, and this one is 3 by 3 is 9t squared. And the last one is just minus y, which is just t cubed. Minus t cubed. Crazy, right? Supposed to be 4e to the power of t. Okay, guys. Well, you see that over here I have a polynomial of third degree. Over here my polynomial is degree 0 in front of e to the power of t. What does it mean, guys? It means that all t's from here except just terms without t supposed to disappear. Let's check if we did any mistakes when we were calculating all our derivatives. So I have t cubed here and I have t cubed here. Good, goes away, right? Now let's do the squares. What I have 9t squared, and 18t squared. This, and this are going to cancel each other. This 2 was pluses and this one was minus. Okay, good. So no t cubes. No t squares. I do have one more t cubed, 3t cubed here and minus 3t cubed here. Cancel them. Last one, 18t from here and 18t from here. And the only thing which is left is just 6, right? So I'm going to write down 6a e to the power of t equals 4e to the power of t. So while comparing these two expressions, I can find that a equals 4 over 6 or 2 over 3. So my particular solution here is 2 over 3 t cubed e to the power of t. I don't want to copy homogeneous solution. What I'm going to do, guys, or I should copy it probably for those people who are kind of, taking their notes. So I'm going to write down general solution. I'm going to copy homogeneous solution. C1 plus C2t plus C3t squared e to the power of t, and add particular solution 2 over 3 t cubed e to the power of t. By the way, guys, in the book they probably will add it into this parenthesis too. Just you're going to be surprised. There are 3 arbitrary constants plus a number here. What would I say? Of course, it's super boring to do all these derivatives, but, well, if our theory is working as we wish, you just need to watch the terms with 0 power of t, because there is no other terms here, right? So basically, you don't even really care what happens to t cubed or anything else. If they are not going to produce you the 0 power of t, then you just don't watch them. You see, from where do we have 0 power of t? Only from here, right? There is no 0 power of t from second derivative, no 0 power of t from first derivative, and of course no 0 power of t from the function itself. Why? Because you differentiate 3 times t cubed together to kill it. You see? Okay, maybe this little advice is going to help you to make less calculations here. I usually use it. Okay, so that was my first example. Now I'm going to move to example number 2. For example number 2, I'm just going to define a particular solution, but I'm not going to calculate the constant. So I'm not going to calculate, like here I calculated A. For example number 2, I'm just going to say, find the form of the solution, but I'm not going to do the constant. Okay, so let me change the color. Example number 2. Find a form of particular solution. Usually it's going to say, do not calculate the coefficients. Do not calculate the coefficients. Okay, so one more complicated equation. We already know tricks over here, right? We're supposed to watch more complicated equation. Y third derivative minus 4 y first derivative equals t plus 3 cosine of t plus e to the power of negative 2t. Well, what is more complicated here is the right side, right? The non-homogeneous part consists out of 3 functions. One is polynomial, one is trigonometric, and one is exponential. Let's see how it's going to work. Remember that we do have superposition principle. So basically, each of these 3 functions is going to produce its own particular solution, which is going to solve the equation. But if you add them together, it's going to solve the whole thing, right? Well, usually we're supposed to start with homogeneous solution because, you see, if we did not do homogeneous solution in the first example, we would end up with what? E to the power of t, e to the power of t, but actually it would not work because it's a part of homogeneous solution. So I'm going to start with finding homogeneous solution. R cubed minus 4r equals to 0, my characteristic equation. This is just R, right? Which is going to give me what? R squared minus 4 equals to 0, and my solutions are 1 is equal to 0, R2 equals to 2, right? And R3 equals to negative 2. So I have 3 different real roots. Let me double check. Yeah. So now I'm going to write down the homogeneous solution. Let me scroll it again up. Oh, but I think we can scroll the whole first example. I don't need this. Yeah, okay. I'm sorry, guys. Sometimes I'm not very good with this whiteboard. It gives me type here, and I don't know how to delete it. Maybe it's going to allow me to delete it. No. Okay. Well, let's leave it here. Okay. So what do we have? Our homogeneous solution y. I pressed something. Homogeneous is going to be what? Well, what is r equals 0? It's c1 e to the power of 0t, right? 0 multiplied by t, and then plus c2 e to the power of 2t and plus c3 e to the power of negative 2t. What is 0 multiplied by t? Is 0, right? E to the power of 0 is 1. So actually my first function is just a constant. c2 e to the power of 2t plus c3 e to the power of negative 2t. Now I'm going to choose a particular solution for each function I have in my right side. I'm going to start with polynomial function. So I'm going to choose y1. y1 is going to work for polynomial function. So guys, normally if you have a polynomial expression of the first degree, it's your particular solution is AT plus B, right? You're supposed to search for particular solution in the same form with the same degree of polynomial, right? But we have one but. This B is not going to work actually because we do have a constant, and the constant is going to work as a solution of homogeneous equation. So when you plug this one into your equation, the B is going to disappear eventually. It's not going to help you to make an equilibrium with T. So what we're supposed to do? Well, our standard method, multiply by T, right? Again, this happens because constant is already a homogeneous solution. If we leave as a constant, it's not going to work. Because B then is, you plug it in here and it disappears. It's going to give you expression about B equals to 0. Well, you probably see it. If you take B, make a third derivative or a first derivative, B disappears from this equation. It doesn't make any sense to add it over here. Okay, good. So we found our first function. Now let's move to the second function. And again, I'm not going to define A and B here, but it's possible to plug everything in and define them, not difficult. Second function is a cosine. Do you have any problems with cosine? Well, homogeneous solution does not have any trigonometry in it, so we're not going to worry about it and just have a standard solution for cosine. We remember that if you do have cosine, you're supposed to also have a sine, right? So it's going to be A cosine of t plus b sine of t. If you are planning to add these two solutions together, you should give different letters here. I'm not planning to add them. I'm just going to write down the final solution is y1, y2 plus y3. But, you know, if you're planning to add them actually as a function somewhere, maybe give different names to the constants. y3. Well, y3 is supposed to be a e to the power of negative 2t, right? But if you look at homogeneous solution over here, we are going to see that this is already solution of homogeneous equation. So we need to multiply it by extra t to make it different. And that's going to be all my functions. So my particular solution here is going to be the sum of y1 plus y2 and plus y3. And if you have half an hour of your time, you can plug everything into the equation and find those constants. Okay, so the last example I want to consider, well, again, I'm considering examples where you can probably have, you know, problems with finding solutions. But normally, you know, if you learned how to do the other problems, like in chapter 3, you're going to be okay with these ones too. So example number 3. So example number 3, y fourth derivative plus 4y second derivative. Remember, when we do have the power in parentheses, it does not mean the power, it means the derivative, right? Sine of 2t plus t e to the power of t and plus 4. Well, what we have, again, we have like 3 different functions. We have exponential, trigonometric, and kind of polynomial, but 0 degree, right? Well, start with homogeneous equation r to the power of 4 plus 4r squared equals 0. Take r squared outside, right, and that's r squared plus 4 equals 0. And what do we have with solutions? r1 and 2 are both 0, so right, r squared here is equal to 0. Here we do have what? r3 equals 2i and r4 equals minus 2i. We'll need to extract the square root of negative 4. Okay, so homogeneous solution. I'm going to scroll a little bit up so I can concentrate on this problem. Homogeneous solution. Why homogeneous? Well, we're going to start with zeros. Remember that it's c1 e to the power of 0t plus c2, because the 0 is multiplied root, we're going to have c1, c2, t e to the power of 0 multiplied by t, right? Plus, these two are going to give us sine and cosine solution, right? Remember that when you have a complex number, lambda is going to give you exponential part of your solution, and mu is going to give you sine cosine frequency. In our case, lambda is equal to 0 and mu is equal to 2. Let me write it down. Lambda plus minus I mu, right? That your complex solution looks like this. Okay, so we do have only plus minus I mu, so mu is equal to 2. So we are going to have, let's say, C3 cosine of 2t plus C4 sine of 2t. That's my homogeneous solution. I'm going to simplify it a little bit. This way we are going to see better what to do with particular solution. So 0 multiplied by t is 0. E to the power of 0 is 1, and I just have a constant C1. Here is going to be like 1, 2, so we are going to have C2t, non-exponential solution. You probably were wondering why non-exponential solution happen when we have 0 as one of the roots, or two roots. Well, these two are going to just stay as they are. Okay, now I'm ready to start picking up my particular solution. Again, I'm going to use superposition principle, and I'm going to start with sine. I do see that sine of 2t is a solution already of homogeneous equation, right? So just sine and cosine is not going to work. I'll need to multiply it by t. So it's going to be, for example, a cosine of 2t plus b sine of 2t. By the way, guys, it does not matter what you put, a here or b here, or switch them, because eventually you are going to find the numbers, and numbers that do not depend how you label them. Okay, so again, we multiply by t because homogeneous solution is marching to the right side. Okay, y2. Exponential function t e to the power of t. Do we have any exponential function here? No. Very good for us. So this t means polynomial of first degree. So actually we are going to write down a t plus b e to the power of t. That's going to be my second solution. And my third solution, looking at 4, I'm supposed to have just a, right, the constant for 0 degree polynomial. But if I look at my homogeneous solution, the constant is already a solution, so I have to multiply it by t, right? And constant multiplied by t is already a solution too, so I'll need to multiply it by t one more time. So my particular solution here is going to be the sum of this y1, y2, and y3. And again, if you guys are planning to really substitute them here, so you probably should use different letters here, or you can label, for example, here A1, B1, here A2, B2, and here A3. Why not? Well, they're still same A, B, and like A, but because they are labeled with different subindexes, they're different. Okay, so, well, we can just, start solving it for coefficients. I'm not going to do this. I'm hoping that you guys can do it on your own. Okay, and that's all for our today's lecture. Okay, I am going to solve one or probably two more problems here in my notes, but that's not going to be like video lecture. I'm just going to put solutions. I think you will be able to go through the solutions without like watching actually it on YouTube, right? Okay, so that's all for this